Right, welcome to this lecture on Runge-Kutta methods. Right, um, the general form of an nth order Runge-Kutta is given by yt plus h minus yt equal to the sum from, say, s equal to 1 up to n of ws by ks, where k1 is nothing but your f t of y, and your ks is given by f t plus as by h, comma y plus h by sum from r equal to 1 up to s minus 1, some beta sr by kr. This is for uh, r equal to 2, 3 all the way up to s. Right, and given let's call this one maybe star here. There. Given your yt plus h, this will be given by what? Your yt plus hy prime t plus h squared y double prime over 2 factorial at t plus all the way up to h to n over n factorial by yn t. The Taylor's expansion of this expression, I can rewrite this as yt plus h minus yt is equal to h y prime, or just drop the t's there for convenience, all the way up to plus hn over n factorial yn. Call this one double star. Right, and we know that y prime is given by f t of y, our initial value problem, so that y double prime is nothing but f prime at t, and your y triple prime is f double prime t of y, and so forth, so that your yn is nothing but f n minus 1 t of y. Right, we can introduce some notation here. For simplicity. Take f to be ft of y, and my partial f partial t to equal to f subscript t partial f partial y will be given by f subscript y, then partial squared f partial t squared given by ft, and partial squared f partial y squared given by fyy partial squared f partial t partial y, which is still equal to partial squared f partial y partial t is equal to f ty or fyt. Right, given this, what else do I need? Now I need to evaluate what is maybe f double prime. Right. For simplicity, maybe let's evaluate y double prime. This is given by what? d dt of your f t of y, so that using the chain rule, this gives me what? Partial f partial t dt dt plus partial f partial y dy dt, but dy dt is equal to what? Y prime, which is equal to f, so that my y double prime is nothing but what? Ft plus f at y. Similarly, my y triple prime will be given by what? Will be equal to d dt of f at t plus d dt of fy. Right, this is nothing but equal to what? Partial ft partial t dt plus partial ft partial y dy dt plus, can have this as f outside by product rule, partial fy partial t dt plus partial fy partial y dy dt plus fy outside now, partial f partial t dt plus partial f partial y dy dt. And clearly this is equal to what? First term here gives me f double t plus f coming from this part by f ty plus f outside of fty plus f fyy from this term here. This is f divided t is f, partial y of fy is fyy plus fy ft plus f fy. Close this bracket here so that this is nothing but ftt plus this term and this one here. They'll add 2 fty plus f squared fyy plus ft fy plus fy squared. So this is my y triple prime. So that's my f triple y. Right, so that to continue, we can look at the order 1, Runge-Kutta order 1, RK1, that is the case when n is equal to 1. So I'm going to get yt plus h minus yt equal to the general case Right, this is going to be given by the case when n is equal to 1 here. So it's going to be h by w1 k1. So this is equal to h by w1 k1. And from double star, we truncate all second order terms, that is h2 terms, so that we are comparing now y prime. But what is y prime? In fact, from this equation here, we can rewrite that as y x t plus h minus yt is equal to hw1 by f, because we defined k1 here. Where's my k1? Defined k1 here. K1 is equal to f. So, and then from this equation here, we have that this is y t plus h minus y t equal to h by y prime. Y prime is f. Right, note that the left hand side of these two are the same, so we can equate the right hand side. This implies h, in fact, let me have this as w1 hf is equal to h by f, and this implies w1 is equal to 1, so that I can rewrite my yt plus h minus yt is equal to h times 1 by k1, but k1 is nothing but f, so this is equal to h by f t of 1, so that you end up with y t plus h is equal to y t plus h by f t of y. So this is our Euler's equation. Or Runge-Kutta order 1. Right. Yes.